bear with me for a moment. So I welcome you all to these help sessions, quote unquote help sessions. Not really help sessions, though we are calling them training sessions. So as Dr. Devaki Adhikari already introduced us to things that what I am talking about and what would be the philosophy of these lectures. So I'd like to again, I'll have to do it all over again. First giving credits to Varshit and Rohan. And now let me talk about chemistry again for camera. This summarizes all chemistry essentially. The concept of things trying to be in the state that they really are. The term for that is stability. Now, what do you guys understand by stability until now? Can I get some answer? What do you guys understand by stability until now? Equilibrium. Okay. Yes, point a term. What do you understand by equilibrium?
Steady state.
Steady state. All right. Steady state is something that I talked about. The state that the system wants to be in. Essentially, what we define stability by is we define stability in terms of energy. That is, if a system is in its low energy state, it's essentially more stable. That is essentially the definition of stability, which is, in my opinion, not very complete, because not all processes, as you say, that happen automatically or states that systems want to be in, like, are dependent upon energy. Say you talk about stay the way it is or it wants to change. Say if I say that something, say I dissolve salt in water, what do you think? It's going to dissolve. It's going to mix around homogeneously and all. And there is this energy also released that you must have heard of, hydration energy and stuff. That energy also gets released. So that is what essentially is ruled by the notion of stability. But when we talk about real world situations, we don't have the factor of just stability, as in stability just gives you the factor of energy. We don't have just energy. We have something called entropy to worry about. For the notion, now I start with the notion of entropy. Entropy is something that tells you about how things want to stay. How things want to stay essentially. Say, if you think about it, say I have an object this way, and if it wants to stay this way, there is only one possible situation in which it can stay intact. But there are a million other ways, or maybe trillions of other ways, that it can potentially break into fragments. Maybe a bit larger fragments. The notion that I am trying to explain here is, probabilistically, in terms of the favorable outcomes, disorder is more favored. In terms of outcomes, disorder is more favored, because there is only one way that it can stay intact, but there are millions of other ways that it can go into a state that is not the way this state is, which it essentially stays in. Which tells you a very interesting fact about universe, that it tends to go to a disorder. It never tends to stay in a singleton state. I'm talking about an order. It doesn't want to stay in an order. That is what is measured by the factor of entropy. And when you go on and look for processes around you, in your nature, you see that multiple processes happen just for the sake of entropy as a factor. Say mixing of gases around you, or maybe you can think of, if I throw this chalk away, it breaks down into pieces. That is also something that essentially tells you about entropy-driven process. A process that is entropy-driven. And for, what do you say, enthalpy, if I think about it, I just throw a log of wood and put fire on it. It gives, if you stand around it, you feel heat. You feel heat. That is essentially a form of energy. So then comes in the notion of stability, because stability is defined in terms of energy. Okay? And then for this energy, this particular energy, we have a term, we have a thermodynamic term that we call enthalpy. Enthalpy is essentially the process specific quantity that tells you about how favorable a process is. Processes in terms of energy of you say the entities involved, energy of the entities involved. Say something is A and it converts to B. The energy of both of these essentially decide enthalpy. And say if a process wants to happen, if a process is favorable to happen, the energy must reduce here in order to the notion of stability that we define. Right. So that is what is essentially defined by enthalpy. And now, when you talk about the real world, when you talk about the world we live in, it's an interplay of both of these. No processes are essentially derived out of just enthalpy or just enthalpy. Some processes like mixing of gases is essentially an example of an entropy driven process. And entropy driven processes where energies don't matter much. Molecules are much far apart anyways. If you think about it in physical terms, you think about potential energy. This is the electrostatic potential energy, and if you think about other expressions of, you say, interaction energy and all, you consider the factor of gravitation. Those potential energy factors, they are essentially null and void in terms of gases, because the molecules are very far apart from each other. That is why the mixing of gases as a process is not enthalpy driven, rather it is entropy driven, because there are a million ways, that million permutations or combinations that the molecules can stay in. That's it. And if I think about enthalpy driven processes, it's about the energy release, as I'm reiterating again and again. Then comes in, this was something that was going on around in the world of thermodynamics for around 50 to 60 odd years, and then comes in Gibbs. Comes up with an equation that quantifies this entropy. Comes up with an equation that quantifies this entropy. Now when I talk about enthalpy, I will be denoting it by H, because historically it was thought as a notion of heat. It was thought of as heat. That is why they chose the symbol H. And when I talk about entropy, I'll choose S. This is something that I'm not very aware about the historical context of, so I would rather not talk about it. Yeah. So then, when they thought of it, they thought of the interplay between them. And say I have a system, and say I have A that is converting into B. You have certain enthalpy here. You have certain enthalpy here. And when I talk about this being, when I talk about H1, the enthalpy of A being more than the enthalpy of B, then I talk about a process that is going from higher energy parameter to a lower energy parameter. That is when I imply mathematically that delta H, that is H2 minus H1, is essentially less than 0. And when I talk about entropy is essentially the measure of how badly you can make a thing, how disordered you can make a thing. So if this talks of disorder, then if we have A and B and we have S1 and S2, we essentially want S2 to be greater than S1. Because of the natural physical world that we observe around us, we want S2 to be greater than S1. And hence we mathematically say that delta S should be positive. And these two things, these might give a hand to each other and they might oppose each other. Then we talk about Gibbs. He comes in and he says, let me take delta H and let me divide out a factor T del S so that it matches the dimension somehow. We just want to match the dimension of enthalpy here for the entropy term, and then he talks about the difference, calls it delta T. Hence you have the Gibbs free energy equation. And this essentially is just about change of changes. This equation is talking about change of changes. These two changes, if both of them lead to a factor that delta G becomes less than 0, this would mean that this term would be this term I would call it negative. This being negative is what we expect for a process to go on itself. We expect this to be negative. This is something, even if it is positive, we have a negative sign. So this term essentially being less than 0 tells you that the process happens by itself. You don't have to drive the process. There are processes that you have to drive by giving them some external push. But these processes happen by themselves. And now, what do we call them? Yeah, that is what I was leading to. A better term than stability would be spontaneity.
Non-spontaneous.
For stability, it doesn't tell you about all the processes happening around you. The energy term wasn't really very relevant in terms of mixing of gases. So you got of this, and when you think of a real world situation, you arrive at the Gibbs free energy. Now, why am I saying that this essentially describes all chemistry? See, the thing is that physics talks about matter in general. In chemistry, we talk about why matter exists in different forms. And I'd like to quote Walter White from Breaking Bad. I'd rather call chemistry being the study of change rather than being the study of matter. So we are interested in how systems want to remain rather than describing a system in general like physicists do. Because then what is the need for chemistry? You could have all these things as a subset of physics in itself. You could have opened a new branch. Why open a new branch in physics? Why do you need chemistry? For this very reason, you need chemistry. Then I'll talk about my next pointer. I'll talk about the physical properties of atoms and molecules. I hope everybody is familiar with the notion of what an atom is and what a molecule is. Yeah. I'll still reiterate though. Anybody would like to reiterate the difference between both of them? Would anybody like that? Reiterate the difference between an atom and a molecule.
Atom is similar and the molecule is made up of more atoms.
Yeah. So could molecules be just atoms as well? Could some molecules just be atoms? Think of such examples. What do you say? If I say I have helium gas, is it an atom or is it a molecule? It's both. So yeah, it goes away. So yeah, so we'll be talking about the physical properties of them. You know about the notion of size from notion of size and all, because that's very logical to think about from what's around you. Now I'll talk about an aspect that is very much which I'll be talking about now. Electronegativity. What do you understand by electronegativity? To per se, get an idea. What do you understand as a layman definition or maybe layman consequence of electronegativity? Anybody would like to volunteer? Tendency to attract the shared pair of electrons. Essentially, you are saying that if say I have something, let me say, if I have an atom A which is in the vicinity of B, I still haven't defined a chemical bond, so I won't say that. Say we have two atoms, and essentially these are lying very close to each other because they are supposed to lie in terms of that Gibbs free energy we talked about. They are supposed to exist that way. They are close to it, and then you see that some electron density is towards one of the atoms and not equally shared between both the atoms. Then you talk of the notion of electronegativity. But how do you think of it? Because you cannot see electrons. You cannot say per se. You cannot physically think of an electron. It's something that's all math. You cannot think of it. You cannot make a physical image of math that's accurate to its real physical interpretation. So, how do I go about thinking electronegativity? How was it essentially established that something like this even exists? How do you know? Now, coming back to physics, that's the way I like to think about chemistry. Go back to physics. Don't think about just chemistry. Go back to physics, because that's essentially what we talked about in the past, maybe half an hour. So yeah, let me go back to physics. Why do charges exist? Why do charges exist? Then we think of, then you might say, and there exist some particles, there exist some electrons. They are talking about a single atom. But how do I tell you about the fact that when you dissolve salt in water, why does it break? Why does salt dissolving in water make it homogeneously distributed all around that media? The reason being that the structure of water, this got to be somehow able to break down that attraction that the molecules of salts have. The common salt that we are talking about. Something has got to break this attraction, as you know from physics that positive charges attract negative charges. That is something we have defined by all those Franklin experiments, and they used to give you those rod and cotton example and all that. We have established that. How do you break a particle? You need something that pulls away this and pulls away this. How do you do that? You need something that has these things. But there are no charges here. There are essentially more real charges here to detect. There are no charged particles here. When you think of a glass of water, you don't think of charged particles floating around. You think of the water molecules floating around. Why would this thing be able to break this attraction? Because there must be some charge development inside each of these molecules. How do you explain that charge development? You think of that some atoms might have the ability to take away electrons, which is essentially the notion of charges. Essentially, there must be something that takes away electrons from one end and causing a deficiency at the other end and causing an excess at one end, which essentially brings us to the point that this is somewhat charged, not exactly charged, but somewhat charged. Then we resort to the principle that we see molecules all around us, and we agree upon something. We discover oxygen, we discover hydrogen, and the with multiple data parameters and all that, we conclude that this thing, this is the thing that is pulling away electrons, which brings up the definition of electronegativity that you guys gave me, taking away electron density from one atom to another. That is what essentially electronegativity is. And now I'd like to address some misconceptions you guys might have from 11th and 12th that about the consequences of electronegativity. Essentially, I'll be discussing about the consequences themselves, but also some misconceptions that you might have from back in the day. Have you heard of this thing called Green's rule?
Yes.
What does it say? What does it say? I have to reiterate myself. Okay. Green's rule talks about bond angles. Green's rule talks about bond angles and tries to relate them somewhat to electronegativity. But how does that work? Nobody told you how an atom being more electronegative or producing the one end of a molecule being more electronegative affects bond angles. Nobody ever bothered to iterate the reason of that. And I have some data for you guys. Now talk about this angle. Think about this molecule. Think about this molecule. Let's talk about this angle. I'm talking about this angle. I'll call it the px angle. When we talk about this angle for PF3, it's 97.8 degrees. These are all computationally calculated. This wasn't the notion how it was thought of historically, but it came up way later in the picture. But this explains a very beautiful thing that is I'm taking it. You have it. You have 101. Why does this thing increase?
Size of the atom, X atoms.
What do you say? What do you say?
Increasing the size of the X atoms.
Yeah, increasing size of X atoms. But also a factor that we are ignoring here is this. The distribution of electrons in these bonds was of this thing being hungry for electrons and this thing being a little less hungry for electrons and this thing being even less hungry of electrons. This bond, if I show it as X, this bond, the electron density of this bond shifts here, which is why it is what do you say? Which is why these atoms can now come closer. This electron density, as it is, what do you say? This is maximum towards the X, as we see in the PF3 molecule. It is maximum towards X. So this thing, this angle here, the atoms can come a lot more closer because electrons repel each other, and if they are pulled to one end and the other end gets a bit free, then these atoms can come even close, which is why this bond angle is very less here and keeps on increasing here as electronegativity decreases. This is a consequence of the fact that we just explained. Yeah.
Shouldn't they be getting farther away because they are getting more electron density? I mean, shouldn't the X atoms be getting farther away because they are more electronegative?
Shouldn't they be going far away?
Yeah, I mean, shouldn't the bond angle be increasing because of the same argument you are making?
Then talking about electron density being shifted, if you think about it, if I think about this bond angle, it's essentially because of let me see. This electron density, if it shifts towards the X atom, because these things are anyways very far away. These things are anyways their clouds are very far away anyways initially. But we are talking about this bond, right? We are talking about this bond angle being there. Can you please restate your question?
I was saying because the electrons are getting more negative on the X side of the atoms.
Yeah.
Shouldn't they repel each other and get farther? The classical Coulomb's law kind of thing.
Yeah, that's what is happening with. That's what is happening here. That's what is essentially happening here. You think about these electrons. If you think about this atom, these were already far enough, and these electrons can polarize on other sides in the 3D space. But if these electrons remain here, because there is one more atom here, because of this extra repulsion of this atom's electrons, these are not free enough. These are not free enough to stay close to each other to get that potential energy thing. These are not free enough to be close to each other, which they become once electrons go away. Once electrons move towards one of the ends, they become free enough to come close to each other. Did you get the answer?
Kind of.
You are kind of getting it. I'll maybe elaborate on it later in the lecture as well. So, we didn't talk exactly about Bend's rule because that's the next example that I'm going to illustrate here. Bend's rule essentially tells you about the electronegativity of the central atom. When this thing gets more, the bond angle also increases. Bond angle also increases. Why is that? If you connect this whole thing on the same line of reasoning, can you implicate that thing as well? If someone would like to volunteer. If you just use the same line of reasoning on a situation like this, then the central atom is changing. This atom I'm talking about, the p atom, if it keeps getting replaced, can you think of the angle of bond, the relation of bond angles? Can you think of it? I have the data for that as well. I'm really sorry guys, I'm fumbling a lot. I'm really sorry for that. I didn't want to do this dry, but I am essentially also doing this for the first time. I haven't taught more than 2 people at a time, so I'm also not a very good orator, to say the least. Now when I think about these molecules, molecules, I have the data here. I don't like to remember numbers, that's why I have it. about explaining this now, taking the same line of reasoning about electron densities along the bond. How do we explain this? If we see through the lens of the same reasoning, the electron density is now going to shift more towards the bond, more towards the inside of the bond, which is why these electrons, or rather the electron cloud, it cannot stay as close as it would if the electron density were away. If the electron density were relatively away, it cannot stay as close as it would have in the case of selenium. Selenium is a lot less electronegative than oxygen, which is what we essentially conclude of these facts only. These very facts is what we use to conclude that electronegativity increases down the group, and all those trends that you hear about, all those exceptions and all. You essentially use the same line of reasoning to conclude that if this electron cloud is more towards oxygen, the bonds can no longer remain as close as they would, which is why the bond angle being that. Bond angle being more than the electronegativity of the central atom is more, and less when the electronegativity of the central atom is less. So now let me talk about something that Dr. Devashish must have talked about as well. If we think about the nucleus here, and if we think about, maybe somewhere at a distance, I cannot draw 3D space on straight 2D board. That is, I'm not doing it. If we think about electrons being at some distance r, this r as it reduces, we say that the electrons are penetrating more into the atom. The electrons are penetrating more into the atom. And this is something that we get from the so-called Schrodinger equation, that we are again and again told about and said that you cannot understand this well, you cannot understand half the concepts well enough just because you don't know quantum chemistry. This R is what you conclude from Schrodinger equation, right? Now, how does this lead to shielding? How does this cause-effect relationship exactly work? If I think of a classical example, draw a nucleus here. I'll just draw it like this. Okay, I don't want to, bring the 3D picture in just right now. If there is an electron here, which is in a space that is closer to the nucleus, by the virtue of the penetration effect that we just talked about. If it is closer to it, there must be an electron after this too. If this electron is too stuck inside, then if you think about it, these electrons have some distance, and by the virtue of Coulomb's law, when we think about Coulomb's law, these two must repel, and this thing is what is attracting it inside. This is attracting this inside too, by the way. But when you think of the interplay between these two effects and connect it to the fact that this is closer to it, so it attracts it more. It is farther away, so it attracts it less, and it also repels. You get to know that this electron and nucleus system, it is not isolated. The interaction is not just between the nucleus and that sole electron. The interaction is about the whole system that we are talking about. Okay, I'll just give it. I'll just after completing this. Okay. So yeah, then just because you cannot just because you cannot very accurately determine these distances, if I talk about it, I call it R0, I call this R1, just for the fact that you cannot determine these very accurately because of quantum effects, because of things like perturbations, you cannot predict them very accurately, which is why you won't be able to comment directly on it. Then you resort to something that chemists usually do, that is empirical observations. Then comes in Slater. Then Slater tells you about, say, this is tells you about something called some factor that you got to subtract for each electron, that gets you to what this interaction actually is, what this interaction is actually quantified as. Then you think about something called as the effective nuclear charge, and the factor that we subtract, what are we subtracting it from? If we thought of this system as just plain A and B, this nucleus being positively charged, this has some Z, and there must be some interaction between them, which essentially gives you the Z. The factor essentially gives you Z. What I am doing is a bit of hand waving is going on behind this thing. When we talk about these charges, these factors, because of being same, they get cancelled out, and hence you are left with this. You are left with just the charges, and after this, the factor that you are subtracting, this is what Slater called shielding constant. Now, why do I call it shielding? I call it shielding just because of the fact that one electron being inside is affecting, or essentially decaying the effect of this central thing on something that is way outside. This is reducing the effect, hence it is kind of shielding. Say someone is shooting arrows at you. You have a ball in front of you, and those arrows essentially, are trying to hit you, and that ball essentially shields you from them. Which this is essentially the notion of effective nuclear charge. I'd like to give a break. Sorry for all that fumbling. I'll continue in the next 5 minutes, and we'll build upon a bit of chemical bonding as well. Yeah. So you are free to have a break. So now I'll be giving a very basic question that you guys know the answer to, but you don't understand the answer to very well, which is why does chemical bonding happen, and what is chemical bonding? We find the answer in the first premise to the lecture that I gave. The subset of which, I would say, the subset of which is stability. That just because of the fact that things are coming close in this context, things are not very far apart for us to literally discard this factor, which we talk about in physics, to literally discard this factor. So we'll rather think about the enthalpy or energy factor more than the entropy factor, which is what motivates us to think about chemical bonding. The historical context of it to think about, you see, you were seeing different kinds of matter, different kinds of things that behaved differently when interacted with each other or maybe the surroundings. Then first came up the concept of what an atom is. Then they saw that some atoms come close to each other, but some atoms stay far apart. Then came up some atoms, if they do not stay far apart, because there is always like if something happens, the contrary is always by far the question of curiosity. You would ask the opposite thing: does that happen or does that not? That do not go far apart. Okay, so when we now think about it, then we come to the notion of something called a molecule. We come to the notion of a molecule. Now, what is a molecule? The exact statement that I gave: atoms don't go far apart. Atoms that don't go far apart. Some atoms go close to each other. Then we think about things like when we think about things like water, when we think about things like oxygen, they are molecules. Now, why are they coming close to each other? If we think about a physical picture, although this is not very physical in the modern context, historically it might have been thought of physically, but at this point we have formalized it so much that it's all math. We don't even see it. So if I think about two atoms that are close to each other, why would they come close in the first place? We have a basic structure of atom in our minds, although that is not very accurate, but we have it in our minds that we have something called positive charges, we have something called negative charges. We have a positive center, negative charges going all around it, and we have another atom with the same thing. Now, because Coulomb's law applies to all charged bodies, this thing is also attracting it. This positive is also attracting the other negative. And then you think about the electrostatic potential energy. That is always inversely proportional to R. All interaction energies by physical laws are inversely proportional to some power of R, which I am thinking of as 1. So, because by the virtue of this, these atoms come close, but this extent varies when you go from one molecule to the other. When you see different things, these charges vary, the sizes vary, the properties that we talked about electronegativity, they vary. This causes a variation in the extent of their proximity. These atoms coming close or going far apart, this affects it. Now, what is the middle ground? What middle ground do we reach after thinking about that positive charge attracting that negative charge, but at the same time that positive charge repelling that positive charge? They must be at some distance from each other, that they stay in the state that they are. That abide by the physical laws that were established empirically or theoretically. Then we think about there being a certain distance between two atoms that are essentially what we call, we take this word directly from English, two things being close to each other and not going away. We call it bonding. Then we talk about a chemical bond. Now, when we talk about the chemical bond, it's not that one atom is going to collide into the other, because of course both of them have positively charged center, both of them have negative charges around them, they are going to repel each other, they are going to stay at some distance, some good amount of distance. So this distance again depends on various parameters, both physical and electronic. And now, when you plot energies, when you build theoretical models to predict energies of this R being this R being more or less, you think about energy of the system, you think about the energy to break them apart, to bring them close, you think about energies. And then when physicists make comparisons between two parameters, what is the first thing they do? They plot a graph. when you plot a graph, we think about energy here, and here is something which I have very loosely called distance for now. This axis is very controversial, I'd rather say. It is in this context I should call it the nuclear coordinate rather than being just the distance. Coordinates essentially give you a notion of distance, but the more apt terminology here would be a nuclear coordinate. Why am I saying that again? Because of these nuclei. These nuclei, if I consider one of these to be 0, then the other stands apart at some distance from it, which is what is essentially going to be useful to us in assessing how a chemical bond forms and how a chemical bond essentially works. Then when physicists plotted using various methods, they stumbled upon this graph. And as I essentially spent the first 15 to 20 minutes on stability being defined as less energy, because that is something that we observe. Things like to stay apart. So things like to stay apart, that is why energy becomes less. And this graph, when we think about minimum energy, it occurs at one minimum point. We have a minima to this graph. We have a global minima to this graph. If you are familiar with mathematics, it's called a global minima. For people not very familiar, I'd rather say that this graph, when you plot it over all these distances, the very minimum value that you get all throughout these distances is the global minima, which is where the least energy lies. I have called it U naught, and the distance corresponding to this is the good old distance that we talked about here. These being at a comfortable distance from each other. This good old distance that we talked about, it is called length. The length of what? The bond that we talked about. This is the very basis of how chemical bond behaves. Right now, because I do prepare after this, so I have a really great question for you guys to ponder about. Have you guys heard of Avogadro's number? Did you ever ask where it came from? Come on guys, please give me some interaction. I'm fumbling a lot, maybe. A factor to that is that you guys are interacting much. I'm very anxious. What kind of experimentation?
I think it came from the definition of AMU, atomic mass unit.
How do you reach that definition?
When we convert grams to AMU, I think it's the reciprocal of that.
So you are essentially talking about the definition that 1/12 of the mass of. This is what you are talking about. But back in the day, nobody had mass spectrometers. Nobody had mass spectrometers to measure the mass of this. There is no weighing balance to weigh a single atom. You cannot even see a single atom. Even if I take a grain of this, it's not a single atom, it's trillions of them. So how do you weigh a carbon 12? There is no way. So there is a very beautiful historical context. It involves ideal gas, talking about thermodynamics. It involves ideal gas laws. It involves essentially